Again, I'd like to welcome you to today's TechNet webcast. This is Designing a Scalable Data Warehouse Business Intelligence System. It's my pleasure to introduce today's presenter. We have Joy Mundy. So Joy, you've got the floor.
Thank you very much. Hi there, I'm Joy Mundy of Kimball Group, and today we're going to talk about how to build a scalable data warehouse business intelligence system on the Microsoft SQL Server platform. Let me begin by introducing my colleague, Warren Thornswaite of Kimball Group. Warren will be answering your questions during and will help me answer your questions after the session. Kimball Group's a small consulting firm that focuses exclusively on data warehousing and business intelligence. We're devoted to education about data warehousing and business intelligence. We write articles and books, and through those books, especially the work of our founder, Ralph Kimball, we've laid the foundation and set the vocabulary for most of the successful data warehouse efforts and technologies today. Our latest book by Warren and me is the Microsoft Data Warehouse Toolkit. And in it, we apply the really popular lifecycle development methodology to the Microsoft SQL Server tools. The information we're presenting today is a tiny subset of the information that's available in that book, as well as in the publicly available classes that we teach. What we're going to talk about today, first is we'll start by discussing what we mean by large scale, and then we'll help you understand where you need to start worrying. I hope and expect that most of you listening today will come away from the session with an understanding of how to think about scalability, how to think about the problems of scale, and what you need to learn to assure yourself and your management that SQL Server will work for your project. This is not a hugely technical session. I'm expecting that you guys understand the basic architecture of data warehousing and business intelligence, what it is, what a relational database is, what ETL means, and so on. In other words, the basic structure of a data warehouse system. I really try to avoid acronyms, but if something I'm saying doesn't make sense, please go ahead and ask a question during the session, and Warren will answer it as soon as he can. For techies in the audience, the session does go into a certain amount of technical detail. I don't have time in an hour to dive deeply into anything, but I do present some areas that we found particularly troublesome and offer a fair number of reasonably technical hints to you that I hope will satisfy the itch for the technical people in the audience. First, we'll talk about what we mean by scale. What are the dimensions of scale? What does large scale mean? Most of the presentation after that is going to be spent on talking about the specific components of Microsoft SQL Server and what you need to worry about in a large scale system. So we'll talk about some design tips for your overall system, and then we'll talk about the relational database, analysis services, integration services, and reporting services specifically. Then we'll finish up with a handful of topics on some of the particular challenges associated with operating a large scale system. When we hear about large systems, we usually hear or often hear only about data volumes. People say, oh, our data warehouse BI system is 10 or 20 terabytes. And that certainly is a valid measure of a data warehouse scale. But there are other kinds of, there are two kinds of data volumes to worry about. The first is how big is the data? So how big is the database? How much historical data do we have in it? And just what is the overall size of the database? The next thing that we have to worry about with data volume is the incremental data volume. And this has as much to do with the ETL process as with the actual database itself. So how challenging is the extract, transformation, and load process? How many rows do we need to worry about? What is the time window that we have to worry about when we're loading the data and processing the data? And of course, finally, how much time and how quickly can we possibly write the cleaned and transformed data into the target data warehouse database? Are we loading 1 million rows a day, 10 million rows, 100 million rows, or more? Scale, though, is more than just data volume, as I've pointed out. One of the other things that we need to worry about quite significantly is the number of users who are using the system. And even more importantly, what are they doing? So it's easy to provide pretty good query performance, or it's fairly easy to provide good query performance on a large database if our users are querying in a predictable way. And the best way to have our users query in a predictable way is to have them use predefined reports. Now, predefined reports, like you can build in reporting services, can be parameterized. They can have drill down paths in them, and they can look to business users almost as if they're ad hoc. But of course, because they're predefined, we know what the queries are that underline the reports, and it's far easier for us to deliver good performance and tune for those predefined reports than it is for ad hoc query use. Some percentage, though, of users need truly ad hoc access. It's usually a fairly small number, like 10 or 20%, but it varies significantly from organization to organization. If your company, by its nature, has a lot of ad hoc users, then you're going to be putting a significant strain on your system. So what from a simply data volume measure looks like a medium system kind of gets bumped up into the large system category if you have an exceptionally large number of users who are doing complicated things on the system. Another dimension of scale is the complexity of the system. By system complexity, I mean several things. First of all, how many subject areas or business processes do you have in your system? An enterprise data warehouse that spans the entire enterprise can have 10 or even 20 interlocking business process dimensional models that contain information about, for example, orders, shipments, finance, and so on. If we look at two data warehouse systems with the same volume of data, if one of them just covers a single subject area, like orders, and the second spans the enterprise and covers a dozen subject areas, it's generally speaking easier to tune the second one because any one subject area and any one table within that large system is probably going to be reasonably sized. If you have just one very large system that covers one subject area, then probably you have one or several extremely large tables, and those are just harder to tune. A final thing that I'm going to mention about system complexity is data latency or frequency of updates. If we populate the data warehouse more frequently than nightly, every day, then we make a quantum leap in the complexity of the system. So again, this is another one of those things that pushes your system, which maybe on the simple measure of data volumes may sound like a medium system. If you have low data latency and are loading the data warehouse in something close to real time, then effectively you're bumping your system up from the medium category to a larger category. What we have here is a polling slide, and what I'm trying to get from you is your sense of SQL Server's limits. I'd like you to select a level in this list that you think is big for SQL Server, that you're not sure SQL Server can do that. And I'm going to show the results for you as they're going. Whoops. Okay, excellent. All right, so a minority of you think that 20 gig is large for SQL Server. A fair number of you think around a terabyte is big. A handful of terabytes is big, and then there are some of you who are reasonably confident that SQL Server can scale to that level, but are less confident about the 10 terabyte level, which is totally fair. So that's very interesting. I'm going to move past that, so I hope you voted. All right, now let's talk about what I think, how big is big, and how you can decide for yourself how you can perhaps update the vote that you gave me on the last slide. So I think the first way to overcome objections to scalability and the best way to overcome objections is to look at real case studies. And you can find several good case studies on the Microsoft SQL Server site, including the two that I've listed here. Barnes & Noble, for example, has 5 terabytes of data storage. It's hard to know what that means, by the way. What does 5 terabytes of data storage mean? But at least we can assume that it's a pretty big database. As they mentioned in the case study, their ETL handles 1 to 3 million rows. Each process is 1 to 3 million rows, and they do that processing and loading in 10 minutes, which I think sounds really good. 10 minutes for 1 to 3 million rows fits within most windows of what we can tolerate on the ETL process. A second really interesting case study is, I should have checked the pronunciation, but Quaylet. Quaylet is a health services organization. Their data warehouse is smaller than Barnes & Noble. It's only 1.5 terabytes, but it's growing by 40 million rows a month. So that's like, what, 1 to 1.5 million rows a day. So that's a reasonable growth rate. But one of the interesting things about this application is that it includes data mining. Now, data mining certainly falls in the category of highly analytical use of a system, or at least the development of a data mining model is a highly analytical use of the system. So it's interesting and very good news that Quaylet is using data mining and is willing to talk about it in their case study. That means that their system, though somewhat smaller perhaps than Barnes & Noble, is doing some really complicated things. And there are many more case study references at the end of the presentation. And you can always go on the Microsoft site, of course, and search for new ones. A second piece of information that we have, a second proof point that we have about scalability is our benchmarks. Now, really the only benchmark that we have is for the relational database. And the one that we use most often is TPCH. And I have the link here to the TPC organization. I looked on the TPC website this morning and got information about how SQL Server is doing in the TPCH benchmarks. Now, first of all, a word about benchmarks. Both the development and the execution of benchmarks tend to be political processes with lots of kind of gaming going on. So they're not, I don't think anyone should make a decision about what technology they buy based solely on a benchmark. However, looking at the benchmarks is informative to us. So we see that Microsoft dominates the 100 gigabyte results in the TPCH sorted by price performance. They have 4 of the top 10 spots in the 1 terabyte results and 3 of the top 10 spots in the 3 terabyte results. And they don't even show up in the 10 terabyte results, which only, by the way, have 4 entries listed, period. So what this tells me is that the relational database is more or less a commodity up to the, I don't know, 3 terabyte, 5 terabytes, somewhere in their level. All the vendors do a fine job in the relational database at that level. Unfortunately, there are no benchmarks like TPC for the other components of the data warehouse system, particularly for ETL, for OLAP, or for reporting. So we don't have an objective or even semi-objective place to go to see how Microsoft technology is doing in those areas. One other piece of information that we have that is hugely valuable is the Project Real information. What Project Real is an internal project at Microsoft that took in several real-world applications and built them in the laboratory. So real means they are real-world applications, but they were replicated in the laboratory using SQL Server 2005. And the guys on the Project Real team have done a very good job of developing best practices and disseminating that information. And anyone who's working on a large-scale system should go to the Project Real website and consume all of the information they have, which is, as I said, excellent. I like pictures, even though I have very few of them in my presentation. And this graphic provides information to you about when you should start worrying about scale. So this is kind of my view about when, with SQL Server 2005, we need to start getting worried about scale. And I'm trying to note that the different rows have to do with data volume, just pure data volume, which is our easiest and most readily available measure of scale. But I'm also talking about usage patterns and number of users. And notice that the scales are a little bit different. So for data volumes, if we have a small data warehouse, less than 50 gig or 100 gig, if we have mostly simple use of the system and not terribly many users, then this is not a large-scale system. This is an easy system, and you can probably just read books online, buy a book, perhaps our book or other books, and basically self-service. In the middle, when we're talking about, I don't know, 500 gigabytes to a terabyte or so, and much more demanding use and many more users, then we need to start getting worried about scale. We need to be very careful about how we put things together and make sure that we and our team is very well educated about SQL Server and the features that will help deliver excellent performance. Finally, on the very high end, when we are talking about terabytes of data, billions and billions of rows, much more demanding usage both in what people are doing and how many people are doing it, then we should be getting experienced help. And at the very high end of the scale, I would encourage you to partner with Microsoft and get their help from the experts that work at Microsoft. Here we have another polling slide. I'm curious to hear how big and how complex are the systems that you guys are working on, both now and over the next, say, 3 years. Okay. Oh. Interesting. Okay, so lots of you are in the small and easy category. And by the way, I love the first two categories, both small and easy and hundreds, but not all that challenging. That's really where I would prefer to be. There's a lot of, it feels like machismo and people who want to be in the terabyte club, but let me assure you, you don't really want to be there. It's really not that much fun. So it sounds like there are a relatively small number of you who are in the very high range, which is what I would expect, and a good chunk of you are on the simple end of the range, and a good chunk of you are in the middle as well. And that is generally what we see in the market, of course. Okay, I'm going to move on. Thank you. All right, now that we've talked sort of generally about scale and what we mean by scale, we're moving on to the meat of the presentation. What I'm going to be talking about next is some overall architectural tips about how we design a large-scale system. And then I'm going to go through each of the major components, SQL Server components that have to do with data warehousing and business intelligence, and give you some tips there. Some of those tips are broad and architectural, and some of them are fairly specific technical tips. So it's a bit of a mix coming up. This slide's probably the most valuable advice that I'm going to offer you in this presentation. First and most important, if you're building a large-scale system, you should get expert help. The single most common source of failure I've seen is to underinvest in technical skill for high-scale systems. Microsoft actually helps you do this, I think, by creating a nice user interface with really helpful wizards, so it looks very easy. But the wizards and the documentations are really focused for the 80% of the market, the 70–80% of the market that doesn't need to worry deeply about scale. If you're at the high end or even the medium end, and you need some, you definitely need some specialized knowledge that's either hard to find or even unavailable in the system documentation. So what I recommend is that you find an expert. Now, luckily, systems in the range of hundreds of gigabytes to several terabytes are no longer exceedingly rare or bleeding edge in SQL Server. You ought to be able to find someone who's done it before and hire them to help you out. If you want to save money, or if it's important to you that your organization develop the skills in-house, you don't have to outsource the complete system design and development, but you can and should at least hire an experienced consultant to do some initial design work and perform a design review. And definitely check their references to make sure they've done this for large-scale systems on SQL Server before. By the way, this is not a plug for Kimball Group. I think I mentioned earlier that we're a very tiny organization. We don't really have the resources to be able to do large-scale system design for many, many companies. My next recommendation, the next advice that I offer, is that you use the features of all the SQL Server business intelligence components. Now, this includes the relational database, analysis services, integration services, and reporting services. There are lots of ways that you can shift processing burden to a different component and deliver an overall system that's more performant. And we'll talk about those techniques in the upcoming slides. My next big architectural recommendation is that you at least consider distributing BI components across multiple servers, either logical servers or physical servers. By doing so, you'll probably reduce efficiency of processors because you're devoting some processors to specific functions rather than sharing them in a pool. But you will increase memory efficiency because different components won't step on each other while trying to grab a lot of memory. There's no hard and fast rule that says you must distribute components in a large system. I'm just saying that you should seriously consider it. Now, my final recommendation is that 64-bit is really, I think, a requirement for high-end systems. All the BI components from the relational database, analysis services, integration services, and reporting services, all the components love memory, and all BI components, by the way, have loved memory since the beginning of data warehousing 20 or 30 years ago. So 64-bit is an obvious recommendation, and the big advantage there, of course, is the large memory address space. It's not particularly anything to do with the 64-bit processor itself. It's really about the large amounts of memory that you can put on the machine. So 64-bit, lots of memory, and things will work much better for you. One of the first things that people need to understand when thinking about the relational data warehouse is understand how to load data fast. And many of you may know this, but it's just so important, and I've spoken to a lot of people who actually don't understand how to load data fast. The first condition is that in order to load data fast, you need to use a bulk load technique. And there are several bulk load techniques. They include the old BCP, which still exists, and also SQL Server Integration Services has destination adapters that also use bulk load techniques. Now, many people think if you just go into Integration Services and you check the checkbox that says fast load, that's going to do a fast load. And it seems like it should, but there are actually underlying conditions that must be met. So checking that checkbox and using a bulk load technique is a necessary but not sufficient condition to loading data fast. In order to load data fast, you also have to be loading data into a table that either has no indexes on it, in which case it can have data, or it has no data in it, in which case it can have indexes. If you think about it, of course, there aren't that many times when that's possible. Before we had partition tables to work with, really, this was only practical during the initial historical load of the system when we were loading up the data warehouse with perhaps the last 3 or 5 or 10 years of history. After that, once the system is up and running, typically we would use a non-fast load technique to add today's or this week's or this month's data into the system. You really do want to be able to use fast load, especially if you're in the situation where you have tens or heavens, hundreds of millions of rows of data that you're adding on every incremental load cycle. You absolutely need to use fast load. And the reason for that is that fast load is way faster than non-fast load. It's like 10 to 100 times faster. Partition tables are a new feature of the Relational Data Warehouse in SQL Server 2005, and they do help us with this fast load problem. So what we're talking about by partition tables is we break a table up into different, effectively into different tables. So we partition horizontally, for example, by month, our fact table, and we have each month in a separate, under the covers, it's a separate physical table. But SQL Server ties those multiple physical tables together into a unified partition table that acts to anyone who's querying or managing the table acts like a single unit. So each partition is stored separately, but it's managed together on your behalf by SQL Server. Now, by managed together, it means it really does look and respond to commands in exactly the same way that a monolithic, a non-partitioned table would do. So you could actually insert, update, and delete on the partition table. If you're in the situation where you need to insert, update, and delete a lot of rows into the partition table, you don't want to do that. You don't want to write an insert statement into the partition table. Instead, you'd use a partition swapping technique. And I don't have enough time today to go into the details on this, but basically what you do is you would load data into an empty partition that is structured identically to your partition table. So because it's an empty partition, you can use a fast load technique on it. You would build indexes on this, I call it a pseudo partition, build indexes on it so that it's indexed exactly the same way as the partitioned table, and then you can swap it in. You just exchange it for one of the partitions that's in the partition table. And the cool thing is that the swap is really, it's nearly instantaneous. It's effectively instantaneous. What's going on under the covers is simply a metadata switch where the partition had been pointing to an old partition that's part of the partition table. Now it's pointing to this new physical entity that you created and stored. So for very large data manipulation processes, you want to use partitioned tables, and you want to do your processing into an empty partition, get everything set up, and swap that partition into the partitioned table. For medium scenarios where you're not actually loading all that much data at any one time, it is common and generally effective enough to actually use an insert into the partition table. So only use this partition swapping technique if you have very large scale issues. If you're trying to load, I would only think about it really if I'm loading somewhere in the area of 1 million rows a day. Probably more like 10 million is where you would start to worry about this. For incremental loads in the hundreds of thousands, depending on your server size and memory allocation and so on, you're probably okay just doing a simple insert into the whole partition table. It won't be a fast load, but it'll probably be fine. The next kind of technical warning that I have for you on the relational database is about partitioning, is about configuring 64-bit memory. And what a lot of people are doing is putting multiple applications or multiple SQL Server instances on the same server, the same 64-bit server. So if you're in this situation, if you have multiple SQL Server instances, I don't mean databases, I mean instances on the same server, or if SQL Server is coexisting on the same server with another memory-intensive application, such as analysis services or integration services or reporting services, then you should definitely place a memory ceiling on each SQL Server instance. And you should also lock pages in memory to prevent operating systems paging of SQL under memory pressure. Operating system paging, if this happens, is such a bad thing for performance that you really need to take the time to investigate this issue and understand how to lock pages in memory and how to place a memory ceiling on the SQL Server instance and make sure that this doesn't happen. On a similar topic, again, when you're running the relational database on a box that has other applications on it, including integration services, you want to use the min and max server memory settings for the SQL Server instance to configure how dynamically the memory is managed by SQL Server. So more dynamic is very appealing. It sounds great. It means that SQL Server balances memory for you. Under constant workloads, it generally works very well. But we've seen problems if other workloads spike their demand. For example, if the relational database is supporting queries and integration services starts up with some kind of processing, then it's going to create a demand for memory. Or if a user launches a killer analytic query. And by killer, I mean just a complicated query that uses a lot of resources. I don't necessarily mean that it's a bad or malformed query, just an expensive query. With a sudden spike in demand from another application, dynamic memory can cause significant performance degradation on the RDBMS. So typically we back off from fully dynamic memory and use less dynamic memory. And again, you do this by manipulating these min and max server memory settings. This means you'll be less efficient in your management of memory. The relational database is guaranteeing its own memory so that it has enough memory to do the work that it needs to do. But that may, under some or even many conditions, may leave insufficient memory for other applications. So these are your levers. It's up to you and your experts to figure out how to set them. But generally, as I said, we pull back from full dynamic memory to somewhat less dynamic memory. Again, in the situation where SQL Server is sharing a server sharing a box with another memory-intensive application, such as integration services, analysis services, or reporting services. Next, we move on to talking about integration services. So first of all, I hope, reassure you that integration services actually works well. And people who are familiar with BTS and SQL Server 2000, which was not particularly scalable, may be skeptical about using integration services in a large-scale system. But integration services is fundamentally different than its predecessor, BTS, and you shouldn't dismiss it out of hand just because you assume it won't scale. It is functional and performs and scales well. The downside to integration services scalability is that there's no magic button that you can push or configuration that you can change that will fix a performance problem that you might have. In general, integration services scalability comes from good design of your integration services packages. And there are way too many design principles to go into here in any depth, but some of the big ones are to parallelize operations within reason. And what I mean by this is it's very easy to set up your integration services system so that you are populating multiple tables at the same time. This is very common with dimension tables. Often we populate 2, 3, 4, depending on how many processors you have on the box, dimension tables simultaneously. And you wait until all the dimension tables have been populated and then kick off one or even more than one, depending on what size server you're using, population for fact tables. Also, within any one package, you might be able to parallelize operations. But my warning here is, and again, there's no magic recommendation or magic button that you can push that will tell you what's going on, but you can over-parallelize. So parallelization up to a certain extent is a good thing, but if you try to set up your system so that too many operations go at the same time, then you're going to see a performance degradation. So just watch perfmon counters, performance monitor counters out in the operating system, and it's pretty easy to see if you're experimenting with it. It's really pretty easy to see when you've crossed that threshold and are trying to do too many things at once. I do want to emphasize two features of integration services that you should be aware of. First, integration services has built-in transforms for sorting and aggregating data within integration services. So these are integration services transforms. Now these transforms perform great. They really perform well up until the point when they don't. So what I mean by this is as long as the stream of data that you're sorting or aggregating fits entirely within memory, then these transforms work very, very well. But when they run out of memory, they have to page out to disk, and then the performance of these transforms really plummets. So if you need to sort or aggregate a very large volume of data, more than will fit in your memory, you should look at another way of doing sorting and aggregation. And the two most common ways of doing it are to plug in a third-party transform that does the same thing. And you can find information about third-party partners for integration services on the Microsoft website. And another very, very common approach is actually to stage the data to a relational table and use the power of the relational engine to perform sorting and aggregation. The next thing that I want to caution you about is the SQL Server destination. Now, the problem with the SQL Server destination adapter, first of all, Books Online, the SQL Server documentation, encourages you to use the SQL Server destination adapter because it is higher performance. And again, it's higher performance up until the point where it's not, and then its performance really falls off a cliff. So the problem with the component, I think there's a flaw in the component, is that it doesn't let you break an insert transaction into multiple commits. So if you're loading billions of rows and you're using the SQL Server destination, it all has to go into the target table, perhaps your data warehouse fact table. It has to go in a single batch. This can create a huge memory pressure on the relational data warehouse server. And then what will happen is that the RDBMS server, the relational server, will, of course, start paging to disk, and you're just not in fast mode anymore. The OLADB destination adapter, that's also part of integration services, does let you commit every so often, like every 10,000 rows or every 100,000 rows. So I strongly recommend that you use the OLADB destination adapter with large-scale data loads. A final recommendation is one we've already made, but it's worth mentioning again, is if you're running into memory pressure with integration services on the same server as the relational database, then you should consider isolating integration services on its own server. Obviously, you'd need good internal bandwidth in order to do this, in order to make this effective, but it's a fairly common thing to do, and again, in the extreme data loading, data processing environment where we're working with millions and millions, tens or certainly hundreds of millions of rows a day. The next issue to discuss on integration services is whether to stage or not stage the data. So our general recommendation, which works well most of the time, is to use the data flow pipeline, which is part of integration services, to do all the transformations. And we want, in general, our strategy is to write or stage data as seldom as possible. So we want to use the data flow pipeline, which operates on sets of data in memory, and do all our transformations in the pipeline in memory and write them to the target table. We don't, in general, want to write or stage data very often at all. But if we take this mandate too far, then we can run into scalability problems. So my recommendation is don't be afraid to stage the data if you need to. In particular, with large-scale problems, it makes a lot of sense to stage updates and deletes to a staging table. So what I'm talking about here is if you need to update, say, 1 million rows in a table, instead of using the data flow pipeline, which is going to do that 1 million rows, a single row at a time, and it's going to be very slow, what you should do is stage those 1 million rows to a staging table, and then use a set operation that will perform, that will either loop over the table and do, say, 100,000 rows at a time. This means more development for you. You need to write a more complex package, but it will be far, far higher performance than using a row-by-row update technique or delete technique from within the data flow pipeline. Another place where staging is extremely useful, and this technique is, by the way, is well documented in the Project Real documentation, is to stage the set of keys that are used today for large lookup operations. So what we're talking about here is on a fact table load, generally when we have a set of transactions coming in for the fact table, the problem is one of the biggest processing problems that we have to deal with in integration services, and in fact in ETL systems in general, is surrogate key lookups. So we have business keys and surrogate keys in our dimension tables, and our fact table we want to end up with surrogate keys. So our fact table, as it's coming into the transformation process, has business keys like account number or product SKU, and we want to look up that business key. We want to do lookups to the dimension tables and return the surrogate key. Now, in any one day's processing, when we're processing the transaction that occurred yesterday, even with a very large data volume, in most cases, we didn't hit all of the dimension members yesterday. So for example, if we are a retail organization, we may have 10, 20, 100 million customers, but probably yesterday at most 1 million of them, 2 million of them actually made a transaction. So what I'm talking about here is a very effective way to improve performance of your processing is to subset the keys that are used, that were actually used yesterday. So you do a pass over the data, strip out the business keys that were actually in the facts yesterday, and then use that to limit the set that is returned by the lookup operation. The reason we want to do that is that the lookup operation performs extremely well as long as the dimension data that's in the lookup, the target data that's in the lookup, fits in memory, fits in cache. With a dimension table that's 10 or certainly 100 million rows, it's very unlikely that we're going to be able to fit all of that in memory. And again, I mentioned already, if you need to sort or aggregate an extremely large volume of data, a very common technique is to stage the data into a staging table and then use the relational database to perform the order by or group by to do that sorting or aggregation. Moving on to analysis services, our basic recommendation is that you attempt to use analysis services for the main user presentation server rather than having business users access the relational database directly, have them access analysis services, and then analysis services is populated from the dimensional relational data warehouse. So in order for this recommendation to work, this means you need to create cubes that are at the same grain as the underlying relational data warehouse. So if you have facts at the order, if you have sales transactions at the order line level in the relational database, then you would have that same grain in the analysis services database, the analysis services cube as well. One of the main reasons, there are many reasons why we suggest to use analysis services for the main user presentation server, but one of the main reasons is that it's easier to tune analysis services for excellent query performance. And this is especially true if there's widely varying or ad hoc use. It's extremely difficult. It is frankly extremely difficult to tune a relational data warehouse, especially at large data volumes, for excellent ad hoc query performance. And that's exactly the problem that analysis services was designed to solve. Now, analysis services includes a number of free techniques, and by free I mean they're just part of the structure. They're just there. They're just features of the product that are available to you. These techniques or technologies include data compression, which improves performance by reducing I/O. Indexing strategies, more sophisticated indexing strategies for a dimensional structure than are available to us in the relational data warehouse, relational database. Analysis services for free gives you aggregate navigation. So one of the best ways to improve performance, and this has always been true again in data warehousing for 20 years, is to predefine and pre-build aggregate tables. So that a query that comes in at a very highly aggregated level, even if the data is at the daily level, a query that comes in at the annual level, at the yearly level, can be answered very quickly by going to a much smaller aggregate table. Analysis services provides this aggregate management and aggregate navigation for you. And finally, analysis services, again, another feature that is in there for free that you don't particularly need to worry about is parallel processing. When we process our analysis services cube, this processing will occur in parallel and is generally very good, generally with very good performance. These are all techniques that you can't particularly tune, but now let's talk about some of the things that you can do to affect the performance of your analysis services database. One of the first things you can do, again, a similar recommendation that I've made already, is to isolate analysis services on its own server. Analysis services loves memory, so letting it be on its own server with its own processors is often a good way to solve a performance problem. Many large-scale customers actually even use two servers, one that handles processing and one that's available for query. And analysis services includes a feature to synchronize the query server with the processing server and flip them over with little or no downtime as far as the business users are concerned. A second huge recommendation is about storage mode. And here the recommendation is that that you store your analysis services database in MOLAP mode. This means that analysis services is managing the entire data, copying the entire data into its proprietary format. Now, many people think that this is an expensive suggestion because it effectively duplicates the data that's in the relational data warehouse. It's in the relational tables, and then analysis services is copying it again into its own file structure. I encourage you to think about this as more of an indexing. When you create an index in the relational database, it also copies the data, and most people don't object to creating relational indexes. But the performance improvement that you get from analysis services MOLAP storage is so significant that it really is our best practice to use MOLAP storage almost always. My next recommendation is that you use analysis services partitions. Analysis services partitions are similar in concept to the relational partitions that we just talked about. You take fact data and you chunk it out by various dimensions. So very often, of course, the first thing we partition by is usually time. So we partition by month or day or week. But analysis services makes it very easy, and in fact, it's a very good idea to partition by more than one dimension. So with a large-scale analysis services database, with many fact rows in it, you want to partition a cube not just by time, but also by a second or even third dimension, such as product brand and customer region. Another lever that we have in improving the performance of the analysis services database is aggregation design. So analysis services manages the aggregations in a way that we can't really touch or manipulate or affect. But the thing that we can affect is which aggregations analysis services creates. And my main recommendation there is that you use usage-based optimization. There are two ways to create or to design aggregations in analysis services. The first simply looks at the structure of the cube and makes an intelligent recommendation about which aggregations to create. And you use this aggregation design when you're first creating the cube. But even before you go live for the first time, when you've been running test data against the system, you should turn on query monitoring and make sure that you're collecting the information that you need to in order to be able to do usage-based optimization. Usage-based optimization, as its name implies, looks at the queries that are going against the system and designs aggregates that will help improve the performance of the system as it's being used by your users. And it's a significant performance improvement over the generic aggregation design that you do when you first design a cube. I also suggest that every so often, perhaps every quarter, you update your usage-based optimization, because as your business evolves, as your business users become more sophisticated, and as the questions that they're addressing change over time, then the aggregations that you want to design for them will also change. So every 3 months is a reasonable frequency for updating the aggregation design for usage-based optimization. And finally, again, I strongly recommend that you hire an expert. There are a ton of little details that you need to do right to make everything work best. And again, analysis services, the wizards and the documentation are really focused on the small to beginning level of medium range of the market of the size of analysis services databases that people are going to be working on. The features are in there to help analysis services scale up to much more significant data volumes. But if you just run the wizard, you're going to be developing a system that is probably not going to perform that well. Some specific tips for analysis services. Of these, actually, the most important one is this one right here. Define attribute relationships between hierarchy levels as appropriate. So I'll talk about that one first. What I mean by attribute relationships is, for you technical people, this is effectively analysis services' way of declaring referential integrity between levels of a dimension. Let me say that again in words that hopefully we can all understand. We create hierarchies that are common drill-down paths in a cube or in the dimensions of a cube. For example, year to quarter to month to day. And of course, a day rolls up to one and only 1 month, and a month rolls up to one and only 1 quarter, and a quarter rolls up to one and only 1 year. When we create a hierarchy, we need to explicitly tell analysis services that these relationships are in place. By default, analysis services doesn't assume that there is any fixed relationship between the levels of a hierarchy. So if, in fact, there is a relationship, we need to declare it to analysis services. So this is a perfect example of what I was talking about earlier about how the user interface leads us down paths that work fine at the small to medium end of the scalability spectrum, but really create issues for us when we're at the very high end of scale. So the default behavior in the UI is to not define attribute relationships. And it's very, very important that we define them in the dimension in order to get good performance. This affects aggregation design, it affects indexing, it affects query strategy. It is just fundamentally important and really hidden in the user interface. A second not nowhere near as important as actually defining the attribute relationships, but still an important nuance is that when you define these relationships, there's a property on them that you can set that by default is set as flexible, I think is the phrase. And if you don't expect the relationship to change, then you should change that property to be rigid. So change the property on the relationship from flexible to rigid. So again, an example of this is, of course, June 20th, 2006 is never going to roll up to anything other than the month June 2006. So that relationship would be rigid. However, if we're thinking about the relationship of a customer to a geography, if a customer lives in California, then we do expect that at some point in the future, it's possible that a customer would move from California to New York. So that relationship you would leave at the default as the default of flexible. A couple of other design tips for analysis services is that you should create several smaller cubes with related measure groups rather than one big cube per database. And this recommendation, again, flies in the face of some of the documentation that you read in books online. What we're talking about here is, remember how I was talking at the, earlier on about how a large enterprise data warehouse may have 10 or 20 interlocked subject areas, business process dimensional marks that are linked together by their dimensions. That same structure you can replicate in analysis services. So you can create one cube that incorporates all of those multiple subject areas. And that's a really nice thing to do because it makes it extremely easy for a business user to perform enterprise-wide analysis that, for example, combines orders data with inventory data. The problem is that very large cube at very large data volumes leads to a performance degradation. So what we recommend that you do is create smaller cubes. If you have a way to break down what business users are going to be doing most of the time, so break down one large cube that may include a dozen subject areas. If you can break that down maybe into 3 or 4 smaller cubes, each of which includes 3 or 4 subject areas, which in the analysis services terminology are called measure groups, then you're going to have a significant performance improvement. Another scalability tip is to use few parent-child hierarchies. A parent-child hierarchy is like an org chart where we have an arbitrary number, an unknown number of levels between the CEO and the peon at the bottom of the chart. Sometimes that could be 1 level, and sometimes it could be 100 levels. Parent-child hierarchies have a reference, a foreign key reference to itself. The dimension table has a foreign key reference to itself, which is where we pick up the parent of any one member. Parent-child hierarchies don't include any intermediate aggregations. So there are aggregations that can be defined at the atomic level, in the case of our org chart, at the employee level of the hierarchy. And we can have aggregations, of course, defined at the entire level, at the entire organization. But there's no way in analysis services, for analysis services to create intermediate aggregations in a parent-child hierarchy. So if you go wild and create lots of large parent-child hierarchies in your analysis services database, then your cube will not perform as well as if you had managed to transform those hierarchies into a more structured, normal, standard hierarchy. Finally, a small recommendation on that affects processing performance is to make sure that you use the OLADB data source when you're populating your analysis services database. In contrast to the .NET data source. You might think the .NET data source would work better because it's newer, but actually the OLADB data source performs much better for populating analysis services databases. My final recommendation on analysis services is to make sure that you predefine analytic expressions in MDX on the server. And my recommendation here has to do with the fact that the way you write MDX affects the performance of the query. So if you take the time to research how to write your MDX, and MDX is the multi-dimensional expressions. It is analysis services analog to the T-SQL query language. If you take the time to research how best to write your analytic expressions so that they perform well, you can store them on the server and make them available to all of your business users, which in itself is a good thing. And by storing it in the server, everyone will be using not only the same expression, but also the same highly performant expression. And that can have, again, really significant impact on the performance of your queries. A quick point on analysis services in the 64-bit on a 64-bit server is that virtual to make sure that you configure the total memory limit for analysis services, and also that you configure the file system cache, which is used by analysis services. Configure the file system cache so that it is trimmed as analysis services is operating. System cache trimming is easy to turn on. It's just something that you turn on, but it is turned off by default. So you need to go into the properties of analysis services and make sure that that's turned on. For reporting services, I have a couple of recommendations. Again, my standard recommendation of if you're having performance problems with reporting services co-hosted on another component of your data warehouse system is to put the reporting services service on its own server. And past that, the second thing that you could do if you're still seeing performance problems is to put report server database on a third machine. Often we put reporting services on its own server, but leave the report server database on the same machine where the data warehouse database is. But again, if you are still running into performance problems on reporting, you should consider putting report server database on a third machine, isolating its workload. And reporting services includes a lot of features for reducing the latency of reports, using snapshots and cached reports to reduce on-demand reporting. I'm almost out of time, but I'm going to run through these last few slides and point out the most important issues of operating a large-scale system. These mostly have to do with backup and recovery. On the relational data warehouse, the most important thing to know is that partition tables really help our backup and recovery story. The reason that partition tables are important for backup and recovery is that each partition can be placed and should be placed on its own file group. And we can set old file groups. So these are file groups for data from last month or last year. We can set old file groups as read-only. Then the backup, the standard relational backup, only backs up the current partition. For example, the current month. So with a data warehouse, a back table that includes 5 years of data, if we only have to back up the current partition, then that obviously makes our backup perform an order of magnitude better than if we have to back up the entire table. On analysis services, my main recommendation here is that the built-in backup does not scale to the high end. So if you have a large analysis services database, you surely are partitioning that database. And the built-in backup facility in analysis services will not back up databases with many, many partitions, so 1,000 partitions or even maybe several hundred partitions. It won't back them up in a reasonable amount of time. So if you have a large-scale analysis services database, you're going to have to need to do file system backup. They're really straightforward. At the database level, it's easy to set up to do it, and you might consider using SAN hardware utilities if your cube is deployed on a SAN. Analysis services can be running during the backup, but you should make sure it's not writing anything. So users can be querying during the backup as long as no processing is going on. And we're over our time, so I am just going to skip the last couple slides and open the floor up for questions.
So Joy, before you actually open up the floor for questions there, it looks like we have quite a few questions coming into the queue. Just want to go through a few call to actions. Looks like there's lots of great information. I do want to point out that you can print a PDF of the slides and get all of these URLs just by going to the File menu. It's in your upper navigation bar. So there's lots of valuable information, like I said, in these slides as well. Did you need to go through these slides at all here in particular, Joy?
No, I don't.
Okay.
These are just there for you to download the deck and take a look at them. They're all available to you on the Microsoft website.
Excellent. I'll just remind you, if you have questions for Joy, I know, like I said, we have a few coming in, and Joy, that's fine. We'll take our time to get through them, and if you can stay around and listen, then that's great. Go ahead and submit those. Use that Ask button in the lower right-hand corner. I want to point out we do record all these webcasts, so if you'd like to see any of our previously recorded webcasts, as well as anything that's coming up, they're all posted right there at Microsoft.com/webcasts. And we'd also love to hear from our audience. So if you have any content ideas or anything that you'd like to see us do differently on these webcasts, let us know, and there's yet another URL posted there. Then I'll just let you know that today's webcast was presented using the Microsoft Office Live Meeting technology. You can get a free 14-day trial. Just go to Microsoft.com/presentlive. And we have a survey coming up. I just want to point out that for filling out that survey, you'll automatically be entered into a drawing to win this 40 GB Creative Zen Ultra MP3 Windows Media Player. And so I wish you luck there. And Warren, go ahead and fill that out too, because you are attending this even though you're answering these questions. So you should be seeing that survey now in your slide area. Go ahead and fill that out while we're going through our questions. And Joy, I'm going to hand it back to you and let you wrap up with what we have in the queue.
Great, thank you. Okay, I have a question from Boone, who asks if we can combine two small cubes and use them for reporting. Again, I ran through the analysis services stuff really fast, but the standard recommendation for an analysis services database is that we define one cube that includes multiple subject areas. So if you're familiar with Analysis Services 2000, you would have created two separate cubes, each of which corresponds to a fact table. In Analysis Services 2005, one cube includes both of those fact tables. So it is very easy, in fact, to combine what you might think of as two small cubes to use them for reporting. But in fact, what you would do is create one cube that includes two measure groups. I have a question from Stuart who says, I have a weekly forecast table of 200,000 rows, which is going to be used in our Analysis Services cube. Does Analysis Services ID all changes? We're considering a daily truncate forecast and reload them all nightly instead of trying to determine what changed. What are my opinions? Excellent question, Stuart. It's really important when you're designing your system to understand that as far as fact data is concerned, Analysis Services cannot process an update or delete. It only can process inserts. The only way to process an update or delete is to fully process the partition that includes the fact row that's updated or deleted. Now, this thing that I'm talking about now about Analysis Services not handling updates or deletes is about fact data. Dimension data is different. Updates and deletes are part of the standard Analysis Services dimension processing. But for facts, we can't update facts that are already in an Analysis Services partition. So the partition story is very important there. If we partition data by month or week or day, whatever the appropriate granularity is, then it's actually very common to fully process the current partition. Once we've finished updating the data that we're working on right now, we create a new partition and fully process one last time, fully process that old partition, and then move on and start, don't touch that partition again and start fully processing only the new partition. So again, processing is done on a partition by partition basis. So if you're not updating or deleting data in aged partitions, then they don't need to be reprocessed. But Enterprise Edition, which supports Analysis Services processing, is really important for this story. Somebody asked how many partitions can be created for good performance. I believe we're talking about Analysis Services here, and I've seen thousands. So with Analysis Services, we want to partition at a very fine granularity. A rule of thumb, which again is just a rule of thumb, is partition should include 10 to 20 million rows. So start thinking about increasing the granularity of your partitioning if any one partition has more than 10 million rows in it. 20 million is a very comfortable number, again, depending on your server technology. This differs, by the way, from the relational database where we are limited. There's a hard limit of 1,000 partitions for a table in the relational database, and we probably don't want to go over 300 or 400. Someone's asking that if we build smaller cubes in 2005, can we do something like virtual cubes in AS2000? Yes, again, this is that issue of building one cube that includes multiple measure groups, and that single cube includes multiple fact data, so it's like that virtual cube in AS2000. Someone asks if we have seen recommendations to put integration services on the same server as the data destination in order to reduce network delays, which seems to go against the recommendation to put integration services on a separate server. Again, putting integration services on a separate server is a useful technique only if you have extremely good bandwidth inside your data center. If you are taking a huge hit in performance by moving the data over to another box, then that is not a sensible thing to do. But a lot of modern data centers have excellent bandwidth internally, so separating integration services onto its own box can be a very effective performance win. Okay. Someone asks, Dan asks about reporting services that generates queries that are large and potentially inefficient. Is there any recommendation? Is there any way to change the queries that it creates? And no, there is no way to change the queries that Report Builder creates. So if you are convinced that the queries it creates are inefficient, and of course that's easy to test, then you would probably avoid using Report Builder with large tables. There are a couple of questions. I'm going to drop off the phone because we need to open up the room for the next session. But I'm going to continue to write answers to the 8 or so questions that remain. So thank you all for listening. And we're going to be muting, and you'll probably get to listen to some music, but I will stick around and will be answering questions in written format. Thank you very much.
Well, thanks, Joy. And I'll just remind everybody that you can watch your inbox tomorrow. I'll have an email with information about viewing this webcast on demand. You'll be able to download it as a Windows Media file. That email will also include a link to the downloadable PowerPoint of today's webcast. So you should all be seeing that survey now in your slide area. I just want to remind you that your feedback is valuable, so take a moment to fill out the survey before you log out. And with that, I'd just like to extend a special thanks to Joy for today's presentation. So that concludes this TechNet Live meeting. I'd like to thank you all for joining us, and our audience may now all disconnect from the audio portion of this event.